Welcome, tech enthusiasts and aspiring Pythonistas. Today, we're unlocking the foundational building blocks of data management in Python, lists and dictionaries. These aren't just abstract concepts, they are the workhorses of almost every application you'll ever build, from simple scripts to complex web services. Understanding how to efficiently store, access, and manipulate data using these structures is absolutely crucial for any software engineer or IT student. Think of data as the lifeblood of your programs. Without proper ways to organize and access it, your code would be chaotic and inefficient. Python provides elegant, built-in solutions for this, and we're about to dive deep into them. We'll explore what they are, how to create them, modify them, and even combine them for powerful data representation. Let's embark on this journey to become data explorers. First, let's talk about lists. Imagine you're making a grocery list. You have several items, perhaps in a particular order, and you might want to add more, cross some off, or even change an item. In Python, a list is precisely that, an ordered collection of items. These items can be of any data type, numbers, strings, even other lists or dictionaries, and a single list can contain a mix of different types. Lists are defined by enclosing their items in square brackets, with items separated by commas. They are changeable or immutable, meaning you can alter their content after they've been created, and they allow duplicate values. For instance, if you have a list of my_fruits, you can easily see how many fruits you have using the len function, or change a specific fruit. This flexibility is what makes lists so incredibly versatile for storing sequences of data where order matters. Once you have a list, the next natural step is to access its individual elements. Python lists are zero-indexed, which means the first element is at index 0, the second at index 1, and so on. Think of it like a row of mailboxes. The first box is number 0, not 1. You can retrieve any item by placing its index inside square brackets after the list's name. But Python offers even more flexibility with indexing. You can use negative indices to access elements from the end of the list. -1 refers to the last item, -2 to the second to last, and so forth. This is incredibly handy when you don't know the exact length of the list but need to get the last few items. It's like reaching into a bag from the bottom without knowing how many items are above the one you want. Beyond individual items, Python lists allow you to extract entire subsections using a powerful feature called slicing. Slicing lets you specify a range of indices to get a new list containing only those elements. The syntax is list, start, end, where start is the beginning index, inclusive, and end is the stopping index, exclusive. This means the element at the end index is not included in the slice. You can also omit start to begin from the very first element, or omit end to go all the way to the end of the list. Even more, creates a full copy of the list. Slicing is an efficient way to work with portions of your data without manually iterating or copying elements one by one, making your code cleaner and faster. One of the most powerful characteristics of Python lists is their mutability. Unlike some other data types, lists can be changed after they are created. You can easily modify an existing element by simply assigning a new value to its index, much like replacing a book on a shelf. Adding new elements is also straightforward. Append adds an item to the very end of the list, while insert, index, item, gives you more control, letting you place an item at any specific position, shifting existing elements to the right. Removing elements offers several options as well. Pop removes and returns an item by its index, or the last item if no index is given. Remove value deletes the first occurrence of a specific value, and the del statement can remove an item by index or even a slice of items. This comprehensive set of methods gives you complete control over your list's contents. Now that we know how to create and modify lists, how do we process every single item efficiently? The answer lies in iteration, specifically using the for loop. The for loop is Python's elegant way of cycling through each element in a sequence. You simply write for item in my_list, and then indent the code block that you want to execute for each item. This allows you to perform operations on every fruit in your my_fruits list, for example, printing them out, performing calculations, or applying transformations. It's a fundamental pattern for working with any collection of data and ensures that your operations are applied uniformly and systematically across your entire dataset, automating tasks that would otherwise be tedious and error-prone. Shifting gears, let's explore dictionaries. While lists are great for ordered sequences, what if you need to store data that has a descriptive label rather than just an index? Imagine a phone book. You don't look up a person by their page number, index, you look them up by their name. This is where dictionaries shine. A dictionary is an unordered collection of key-value pairs. Each unique key maps to a specific value, much like a word in a dictionary maps to its definition. Keys must be unique and immutable, like strings, numbers, or tuples, while values can be anything at all, strings, numbers, lists, or even other dictionaries. Dictionaries are defined using curly braces, with key-value pairs separated by colons, key, value, and individual pairs separated by commas. They are also mutable, meaning you can change their contents after creation. Accessing data in dictionaries is intuitive and mirrors the real-world concept of looking things up by name. Instead of an index, you use the associated key within square brackets to retrieve its corresponding value. So, person_details, name, would give you the person's name. However, a common pitfall is trying to access a key that doesn't exist, which will result in a key error. To guard against this, Python provides the .get method. Person_details.get city will return the city if the key exists, but if city is not found, it will return none by default, or a value you specify, like person_details.get country unknown. This makes your code more robust and less prone to crashes when dealing with potentially incomplete data. Like lists, dictionaries are dynamic and fully mutable. Adding a new key-value pair is as simple as assigning a value to a new key, my_dict, new_key, equals new_value. If the key already exists, this same syntax will simply update its associated value. This makes dictionaries incredibly flexible for building dynamic profiles or configurations. Removing key-value pairs also has a few options. The pop key method removes the item with the specified key and returns its value, which can be useful if you need to use that value after removal. Alternatively, the del statement allows you to remove a key-value pair directly by referencing the key, del my_dict, key. These operations allow you to keep your dictionary data current and relevant as your program executes. Iterating through dictionaries might seem a bit different from lists because of the key-value structure, but Python offers versatile ways to do it. You can iterate directly over the keys using a for loop, as keys are the default when looping a dictionary directly, for key and person_details. For explicit clarity, or if you only need the keys, you can use person_details.keys. If you only care about the values, person_details.values will give you an iterable of all the values. And for the most common scenario, needing both the key and the value, person_details.items returns a view of key-value pairs as tuples, allowing you to unpack them directly in your for loop like for key, value and person_details.items. This flexibility ensures you can always access precisely the data you need for processing. The real power of lists and dictionaries often comes when they are used together. A very common and powerful pattern in programming is to have a list of dictionaries, where each dictionary represents a distinct record or object. For example, you might have a list of students, where each student is a dictionary containing their ID, name, and grade. This structure is incredibly versatile and closely mirrors how data is often represented in databases, JSON files, and API responses. Accessing data in such nested structures is straightforward. You first access the dictionary within the list using its index, and then access the specific value within that dictionary using its key. This allows for complex data modeling and efficient retrieval of specific information from large datasets. Understanding lists and dictionaries means you've grasped the fundamental ways Python handles collections of data. Lists excel when you need an ordered sequence, allowing for fast access by position and dynamic resizing. Dictionaries are unparalleled when you need to store and retrieve data based on unique identifiers or labels, providing efficient lookups. Together, they form a robust toolkit for managing almost any kind of data your programs will encounter. From parsing JSON responses from web APIs, representing user profiles in an application, or structuring configuration files, these data structures are your go-to solutions. They are not just theoretical constructs, they are practical, everyday tools that will make your Python code more readable, efficient, and powerful. And that wraps up our deep dive into Python's lists and dictionaries. You now have a solid understanding of how to create, manipulate, and iterate through these essential data structures. The concepts we've covered today are critical for building any non-trivial Python application. Remember, practice is key. Head over to the PY Data Explorer